morning, everyone. Today we will start a new topic. Today we will enter the second part, Martingale. So today we will talk about what is a probability space, conditional expectation, Martingale stopping time, and optional stopping theorem. So what is a probability space? In fact, you have informally meet with this notion of probability space several times. Here, just to summarize what is the mathematical background for this probability space. For a probability space, when we say a probability space, there are usually three ingredients. First, omega is called a state space. Second, F is a sigma algebra. And the third ingredient is a probability measure. So here, omega is just a set. And F is a sigma algebra. So what is a sigma algebra? F is a sigma algebra. It is just a collection of subsets of omega and satisfying the three properties. First, the whole space is in this sigma algebra. Second, for any event F in this sigma algebra, its complement is also contained in the sigma algebra. And third is countable union is still contained in this collection. So if we have a countable collection of events, then the union of them is still contained in this collection. So a collection of subsets of omega satisfy these three properties, then we call this a sigma algebra. And omega together with the sigma algebra is called a measurable space. And the third ingredient is called probability measure. So P is a probability measure. It is a function defined on the sigma algebra, and to real numbers satisfy the following property. Okay, so first, of course, for empty set, it should have zero probability. And for the whole space, it has mass 1. And the second property is, if we have a countable collection of disjoint sets, so Fn is countable collection of disjoint sets, then the summation of probability for all these events equals the probability of union of all these events. So a probability measure should satisfy these two properties. So just to give a quick example. So suppose X is a Bernoulli random variable with probability P. So it means that this X takes value +1 with probability P and -1 with probability 1 minus P. Then for this random variable, the corresponding sigma algebra F has 4 events: empty, whole space, X equals 1, and X equals -1. So this is the corresponding sigma algebra. And then the corresponding probability measure defined on the sigma algebra is empty set equals 0, the whole space equals 1. And for this event, it equals P. And for this event, it equals 1 minus P. And we can easily check that this probability satisfies this relation here, because in fact we don't have countable so many disjoint sets, we only have these 4 events. Okay, so this is the first example for Bernoulli random variable. A second example is for a uniform random variable. So suppose X is a random variable that is a uniform on the unit interval, then the corresponding sigma algebra is generated by all events look like this. So by this notation, I mean, in this collection, it contains all these events. And the sigma of this collection means this is the sigma algebra generated by this collection of events. So this is the corresponding sigma algebra for this random variable x. And then the corresponding probability measure is given by this one. Here we can also check that by definition, this probability measure also satisfies the relation here. So suppose that In is a countable collection of disjoint intervals. Then here we see that the event of probability that x is containing In equals the length of In. And then if we take, and here we can see that since In is they are disjoint intervals, then the event x in In, this is also a disjoint sequence of events. And for this disjoint sequence of events, we see that the probability of x in In summing over n. We know it is the total length of In, and this is exactly the same as the probability that x is the union of x in In. And this is the same as the probability that x is containing the union of In. Okay, so this is just a quick recall of what is a probability space. So for a probability space, we have three ingredients. First, omega is called a state space. Second, F is a sigma algebra. And third ingredient is a probability measure defined on the sigma algebra. Okay, probability space. And then we can turn to what is a conditional expectation. So on this page, the information is not precise. I just give you a motivation of why we define conditional expectation in the following way. So we know this is elementary conditional probability. So suppose we have two random variables, x and z. And they take value in a discrete space. We know how to calculate what's the conditional probability that big X equals a state given Z equals a state. So this is an elementary conditional probability. We know that this guy equals the probability of the union of the intersection of the two, normalized by the probability that Z equals Z. So this is an elementary conditional probability. Given this notion, we can define an elementary conditional expectation. So what is the expectation of X, knowing that Z equals small z? So we can define in the most naive way is we can define conditional expectation in this way. So this is consistent with elementary conditional probability. And so the question is, from this point of view, in fact, what we want to do is we want to calculate what is the expectation. Suppose that we know all the information of Z. So here just we know that Z equals one of the states small z. And my question is, so then what is the conditional probability that given all information of this random variable Z? So now we want to define a quantity Y. It is the expectation of X, but suppose that we know all the information about this random variable Z. So how should we define this quantity? So first of all, because this Y is the expectation of X, knowing what happens to random variable Z, so this Y should be measurable with respect to the information of Z. Second, from the elementary conditional probability here, we see that if this Y is a conditional, is the expectation of X giving all the information of Z, of course it should coincide with what we have here. So it should be consistent with the elementary conditional expectation. So precisely, we must have that this y restricted to some information on z equals x restricted to this information on z. So this is what we have from elementary conditional probability. So for elementary probability, we know that this is the elementary conditional probability. So roughly, naively, we can define a conditional expectation in this way. And now suppose that we want to define expectation of x knowing all the information of this z. Then a natural way for this guy is, first of all, it should be measurable with respect to all the information of the z. And second, given any restricted to any event that depending on this big z, the expectation of this guy should equal the expectation of x. Okay, so this is just a motivation of conditional expectation from elementary conditional probability. And next, we can introduce what is a precise conditional expectation in the language of real analysis. So first, suppose that this is a probability space. And x is a random variable on this probability space such that it has finite expectation. And then A is a sub-sigma algebra. So this sub-sigma algebra, I mean that this A is a subset of F, and A itself is also a sigma algebra. And then we want to define the conditional, the expectation of X, knowing all the information in A. And then the definition is, there exists a unique random variable y with the following two properties. First, y is A-measurable. And y has finite expectation. Second, for any event in A, we have expectation of y restricted to A equals the expectation of x restricted to A. So this is a formal definition of conditional expectation. Here we can see that it is consistent with our motivation from the elementary conditional probability. First is conditional expectation should be measurable with respect to the information we know, because we want to calculate the expectation given all this information here. So first, it should be measurable with all the information we know. Second, if we restrict it to any event in the information we know, then the restricted expectation should be the same as x. Okay. And another part of the conclusion of this definition is, if y tilde is another random variable satisfy these two properties, then this y tilde equals y almost surely. So moreover, okay, if y tilde is another random variable with these two properties, then it equals y almost surely. So this part, so for this definition, so on the one hand, you can view this is a definition for conditional expectation. In fact, it is also theorem. This theorem says, first of all, there exists such a random variable satisfy these two properties. And the second part, in fact, there is a unique random variable satisfy these two properties. And the third part is we define this random variable as our conditional expectation. Okay, so the proof of this theorem is in the lecture notes, and I recommend you to read the proof after the lectures. I won't prove this theorem here. So here, from this theorem, finally we define that this random variable as the conditional expectation given all information in A. So this is the formal definition of conditional expectation. Just a quick remark. From this definition, we can have some direct consequences. So first, it is consistent with expectation if this information A has no information. So if our sigma algebra A only contains empty set and whole space, so of course this is a sigma algebra. And if we repeat the definition here, we can see that the conditional expectation is exactly the expectation. So it's just a real number. So this is consistent with our intuition. So if we have no information at all, then the expectation is just the expectation, and this is a real number. So we don't have any information at all. Second, if we already know that this x is A measurable, so it is measurable with respect to A, then the conditional expectation is this random variable itself. So first, why this is true? Suppose we want to calculate the conditional expectation here, and this is x. And let us check x satisfies these two properties. First, x is A measurable because we assume that this x is A measurable. Second, this x also satisfies the second condition here. So of course, because here is the same as s, and here is the same as x. So if x is A measurable, the conditional expectation is itself. And this is also consistent with our intuition because now this is all the information we know. And we know that x is measurable with respect to this information. Of course, we already know what is x because we know the information in A. So the conditional expectation is the random variable itself. Finally, suppose that y is a conditional expectation defined in this way. We always have that the expectation of this y equals the expectation of x. So why this is true, just from the definition here. Okay, so we know that y is the conditional expectation, so it is the random variable with these two properties. Now, here if we take A as the whole space, then the left-hand side is the expectation of y, and the right-hand side is the expectation of x. So for conditional expectation, y, we know that the expectation is always the same as the original random variable. So this is the conditional expectation. Do you have any question? Okay, so this is the definition. If there's no question, we'll turn to the basic property of conditional expectation. So in these 2 pages, roughly speaking, we say that the basic properties that is right for expectation, they are also right for conditional expectation. Okay, so first, linearity. So if we have 2 random variables, x1 and x2, and 2 constants, linearity. So xy and x2 are 2 random variables. a1 and a2 are 2 constants. Then for ordinary expectation, we know that the expectation is linear. this is true. This is linearity for ordinary expectation. And the first conclusion is this is also true for conditional expectation. So if we take conditional expectation, this is still true. Okay, so the proof of linearity is left as exercises. Okay, so this is the linearity. Second is positivity. So the positivity says, if the random variable is non-negative almost surely, then for ordinary expectation, we know that the ordinary expectation is non-negative. And this is also true for conditional expectation. Okay, I will give a short proof for this positivity. So why, if the random variable is non-negative, and then the conditional expectation is also non-negative? So here, in fact, from now on, by now, we only know the definition of conditional expectation and nothing else. So to prove basic properties, we can only use the definition. So suppose y is the conditional expectation, and we want to show that it is non-negative almost surely. Why this is true? By definition, we know that for any event A in the sigma algebra, we know that the expectation of y restricted to A equals the expectation of x restricted to A. This is from definition of conditional expectation. And since x is positive, it's non-negative almost surely, x times this indicator function is also positive, non-negative almost surely. So the expectation is non-negative almost surely. So we know that, so from the definition of conditional expectation, we know that for any event A in this sigma algebra, the expectation of y restricted to A is always positive. So this is just what we have from the definition. And then we want to show that this y is non-negative almost surely. So in other words, we want to show that the probability for this y is negative is 0. Okay, so we define an event an. So it is the event that y is less than -1/n, so it is negative. And since y is a measurable, so y is a measurable, so we know that this an is contained in the sigma algebra A. Since an is contained in sigma algebra A, from the relation here, we know that the expectation times indicator on an is always non-negative. So from the relation here. But on the other hand, we know that on this an, this y is less than -1/n. So this guy is less than -1/n times the probability of PAN. So now some negative quantity times the probability is positive. This is only possible that the probability equals 0. And this is true for any n. So this implies that the probability for the union of an is also 0. And the union of an is exactly the probability that y is negative. So the probability for y is negative is 0. So this means y is positive, is non-negative almost surely. Okay, so this is positivity. So you can just remember that the property for that is true for ordinary expectation is also true for conditional expectation. Okay, positivity. And the third property is monotone convergence theorem. So for monotone convergence theorem for ordinary random variable, what we know is if we have a sequence of random variable converges to another random variable almost surely, then we know that the expectation will also converge. So this is monotone convergence theorem for ordinary expectation. And the conclusion here is also true for conditional expectation. So if a sequence of random variable is increasing to x almost surely, then the conditional expectation also converges to the conditional expectation. So why this is true? So if we define yn as the conditional expectation of xn, so since xn is increasing, so we know that xn plus 1 is greater than xn, so xn plus 1 minus xn is positive. And by positivity, this tells us yn plus 1 is greater than yn almost surely. So this is true. This is true by positivity. So this tells us if xn is increasing, then this yn is also increasing. So yn is also an increasing sequence. And since this is an increasing non-negative sequence, we can define y as its limit. So this is an almost sure limit. And then the only remaining thing we want to show is, so here the conclusion is we want to show yn converges almost surely to the conditional expectation of x. And here we already know that yn converges to something almost surely. So it is sufficient, it is only remaining to show that. So we only need to show that this something equals the conditional expectation of x. So we need to show that this y, so this y is defined as a limit, equals the conditional expectation of x. So we want to show something equals the conditional expectation, and the only thing we can use is the definition. So if we want to show that this y is the conditional expectation, we need to check that this y satisfies these two properties. So first, we know that yn is a measurable. And y is the almost sure limit of yn. So this implies that y is also a measurable. Okay, so we have already checked the first condition. And then we need to check the second condition. So for any event A in the sigma algebra, we need to show that the expectation of y restricted to A equals the expectation of x restricted to A. So what is this guy? The only thing we know is y is the almost sure limit of yn. And this yn is positive consequence. So by monotone convergence theorem for ordinary expectation, we know that this is the limit so this one equals this guy is by monotone convergence theorem for ordinary expectation. And then by the definition of yn, because yn is the conditional expectation of xn, so by definition of yn, we know that this equals xn restricted to A. And finally, we apply monotone convergence theorem for ordinary expectation again. This tells us this equals x restricted to A. So this checks that our random variable y satisfies the second condition. So the conclusion is y equals the conditional expectation almost surely. This is monotone convergence theorem. Okay, so other property. The next one is called Fadou's lemma. Okay, Fadou's lemma. Fadou's lemma tells us if we have a sequence of non-negative random variable, then the expectation of limit inf is less than the limit inf of the expectation. This is Fadou's lemma for ordinary expectation, and the conclusion here is this is also true for conditional expectation. Okay, and in fact, you can prove this Fadou's lemma in a similar way as monotone convergence theorem. The next property is dominated convergence theorem. So for dominated convergence theorem, it says that if we have a sequence of random variable xn, and it is dominated by a random variable that is finite, that is in R1, so it has finite expectation, then we know that limit in. So maybe okay. So it is dominated by a random variable, and it has almost a sure convergence. Then we have that the expectation of the ordinary expectation will converge to the ordinary expectation of x. And here, the same is true. So the same conclusion is also true for conditional expectation. Okay, so proof of Fadou's lemma and dominated convergence theorem are left as exercises. The last basic property is Jensen's inequality. So for Jensen's inequality, it says that for any convex function, we have the expectation of phi x is greater than the phi of the expectation. So this is the Jensen's inequality for ordinary expectation. And the conclusion is this is also true for conditional expectation. I will give a quick proof of why this Jensen's inequality is also true for conditional expectation. So first, recall some basic property of convex function. So phi is convex. The definition is, so the definition for convexity is for any alpha in 0 and 1. So it means that the linear combination of these two points x and y and then we composed it with this function phi is greater than we first composed with phi, and then take a linear combination. So the idea is, if phi is convex, then this point is x. Yes. So this point is x, and this is point y. If we first take a linear combination between x and y, so suppose we are at some point here. Convex, wait. Convex. First x and then, okay, sorry, this is convex. Okay, so it says that if we first take a linear combination between x and y, suppose this is the linear combination of x and y, and then phi x is here. Phi of this point is here. And then on another way, if we first take phi x and phi y, and we take a linear combination of this point, then the corresponding point is here. So this is always greater than the other case. So this is convex function. And for convex function, we have a characterization. So roughly speaking, a convex function can be approximated by linear combination. So there is a characterization for convex function says there exists a sequence of pair of real numbers a and bn such that so this is a special property that is true for convex functions. So roughly speaking, it can be approximated by linear combination of linear functions. Okay, this is a quick recall of convex function, and then why the Jensen's inequality is also true for conditional expectation. Okay, so for conditional expectation, first of all, suppose this is sequence an and bn satisfy this property here, then what we know is for any n, phi x is greater than this linear combination. It's greater than an times x plus bn for any x. And then by positivity, we know that, so by positivity, we know that the expectation, conditional expectation of phi x will be always greater than an times the conditional expectation plus bn, almost surely. So by positivity, we know that this is true almost surely. So for any n, this is true almost surely. And since we only have a countably many n, so we can also say that this is true for any n almost surely. So first we put n outside, and now we put n inside this almost surely. Since this is true for any n almost surely, we can take sup here. So this is also true almost surely. And then for the right-hand side, because of this characterization of convex function, we know that the right-hand side equals exactly phi of the quantity here. So this shows that if we first take phi and then take conditional expectation, this is always greater than first take expectation and then take this composed with a convex function. So this is the proof that says that Jensen's inequality is also true for conditional expectation. Okay, so this is the basic property of conditional expectation. And on this page, we will talk about what happens when we have two different subsegment algebras.
Sorry, just one thing. When you wrote the definition of convex, the first thing you wrote is that it's actually smaller than the linear function, the one defined by alpha px plus 1 minus alpha.
Yes.
And then you're saying for every a, b, n, it's bigger than linear function?
Yeah.
But this alpha pi x plus 1 minus alpha pi y, it's a linear function too.
No, but you draw the tangent.
So roughly speaking, the graph function, the convex function have a graph look like this. And then the an x plus b, and it just corresponds to the tangent line here.
Ah, okay.
So it is the supremum over all this tangent line, roughly speaking. Okay. So this is the basic property for conditional expectation, and for all these properties, we fix our subsegment algebra. And on this page, we will talk about what happens when we change the segment algebra. So the first property is called Taylor's law. So here we have two Taylor property. Okay, property. So here we consider we have two subsegment algebra, and one is bigger and another one is smaller. So we have two subsegment algebra, A and B. And A is smaller, B is bigger. Okay, so I want to keep the same notation as on the slides. So here is B is smaller, A is bigger. Okay, so the Taylor property tells us we first take conditional expectation with respect to A. So, and then we take conditional expectation with respect to B. This is the same as we take conditional expectation directly with respect to B. Okay, so before we prove this property, what does this say? So first, A is greater than B, means A contains more information. We take conditional expectation first with respect to A. So we get something that is measurable with respect to A. And then we take conditional expectation with respect to B. So in this process, we lose some information. And this Taylor property tells us this is exactly the same as if we just take conditional expectation with respect to B directly. So here we just, first we know this X, and then we lose some information to get conditional expectation with respect to A. And then we lose some information to get conditional with respect to B. And this is exactly the same if we take conditional expectation directly from B. So this is the Taylor property. So why this is true? So I denote Y as the conditional expectation here. Y as which one? A. And this relation, so we want to show that so we need to show that the conditional expectation of Y given B is the same as conditional expectation of X given B. So now we want to show that this guy is the condition of X given B. So we need to check this guy satisfies the relation here. So first, it is B measurable, of course, because this is definition for conditional expectation. And then we need to check the second property. So for the second property, what do we need to show is for any event B in this sigma algebra, this guy so the expectation of this guy restricted to this event should be the same as the expectation of X restricted to this event. So this is the second condition we need to check. For the second condition, why this is true. Okay, so first, let us check what is the left-hand side. What is the left-hand side? So the left-hand side is, this guy is the conditional expectation of Y given B. And this is an event in B. What to do? Is B measurable? Maybe it is easier to check what is the right-hand side first. Okay, right-hand side. So for the right-hand side, it is X restricted to B. And by definition, we know that this B is contained in B and is also contained in A. So by definition of conditional expectation with respect to A, we know that this equals Y restricted to B. Because this B is contained in A. So since B is contained in A, and Y is the conditional expectation of X given A, so this one equals this one. This is the right-hand side. And for the left-hand side, So for the left-hand side, we know that this guy is the conditional expectation of Y with respect to B. And now we time it with the event in B. So by definition of conditional expectation, we know that this is exactly as Y times the expectation of Y restricted to B. So from here to here, we use the definition of So from here to here, we use the definition of conditional expectation of Y with respect to B. And from here to here, the thing we use is the definition of Y, which is the expectation of X given A. So this is a difference from the left-hand side and the right-hand side. But finally, they prove that the left-hand side equals the right-hand side. So this is the tower property. So for the tower property, it tells us if we calculate the conditional expectation first with respect to a larger sigma algebra and then a smaller one. So this is the same as we calculate that conditional expectation directly with the smaller one. And another remark, so if we switch the role of A and B here, the equation is still true. Can you tell me why this is true?
Because it's immeasurable.
Yeah. So if we just switch the role of A and B, this guy is already B measurable. And B is contained in A, so of course it is also A measurable. And since it is A measurable, then given A, we want to calculate the conditional expectation of a guy. This guy it equals itself almost surely. Okay, so this is tower property. The next property is called taking out what is known. So it says that if we have a random variable z is a measurable, then we calculate the conditional expectation of x times z given A. It equals z times the conditional expectation of x given A. So roughly speaking, why this is true? So here z is a measurable, and when we calculate the conditional expectation, this notation means we know all the information in A, and we calculate the expectation of this guy. Since z is already a measurable, so we know what is this z. So it just corresponds to a constant when we calculate the conditional expectation. So of course we can put it outside. So this is why it is called taking out what is known. So because the z is already known, of course we can put it outside the expectation. Okay, so why this is true? So first, if z is an indicator function, so if z equals indicator function for some A in this event, then we already know that this indicator function can be taken outside. You can check this directly by the definition of conditional expectation. So if A is an indicator function, then this is true. And then if A is a linear combination of indicator function, this is also true. Then this equation is also true. And finally, for any z, we can approximate z by linear combination of indicators. And then by dominated convergence theorem for conditional expectation, we can also check that this equation is true for any z that is a measurable and is bounded. Okay, so this is taking out what is known. And the last property is called independence. So here it says that suppose that B is a sigma algebra such that it is independent of the sigma algebra generated by X and N. So it is independent of X, and it is also independent of information in A. And then we want to calculate conditional expectation of X given A and B. And it says that this is the same as condition of X given A. So roughly speaking, it means that this B is independent of X. Of course, if we know information in B, it doesn't help us to calculate the expectation because it is independent of B, independent of X. So it is the same as the conditional expectation if we don't know anything about B because it is independent of what we are interested. So this is the intuitive idea of what is this equation tell us. So proof. So before the proof, in particular, if we set A equals the trivial algebra, so in particular, if A is the trivial algebra, then this equation tells us this equation will become this one, and this one, it says that we calculate the conditional expectation giving all the information in B. Then this is the same as the expectation itself. And this is also consistent with our intuition because B is independent of X. So knowing information in this guy doesn't help us to predict what is X. So it is still this real number because it is independent. Okay, so this is what this independence tells us. So why this is true? So now we prove this equation here. So what is the left-hand side? So the left-hand side is the conditional expectation given A and B. And the right-hand side is, we call the right-hand side as Y. And now, in fact, what we need to show that Y equals the expectation of X, knowing A and B. So why this is true? So now we want to show that this guy equals the conditional expectation. We only need to check the two properties. First, this Y is sigma AB measurable. This is true because Y is already A measurable. Of course, it is also AB measurable. And second, we need to check that for any event C in the sigma algebra, whether we have so we need to check the second condition. So for any event C in the sigma algebra generated by A and B, why we have the relation here. And this is sufficient. It is sufficient to show that so to show this condition, it is sufficient to check for the event C, which is the intersection of A and B, because this A is in A and B is in B, because linear combination of this kind of indicator function will generate the whole sigma algebra. So it is sufficient to check this, whether this is true for this particular kind of C. So now let us check whether it is true. So whether this is true. For the left-hand side, what we have is, this is Y times A and times B. And we know that Y is the expectation of X given A. So first, we know that Y is a measurable, because Y is the conditional expectation of X given A. And then we know that this A is independent of B, because B is independent of X and is also independent of A. So this tells us Y is independent of this event B. And of course, A is also independent of this B. So Y is independent of B, and A is also independent of B. So now the left-hand side will become the expectation of Y restricted to A times the probability of B, because B is independent of these two guys. This is the left-hand side. And for the right-hand side, so this tells us B is independent of X times 1A. So it is independent of this guy. So the right-hand side equals expectation of X restricted to A times the probability of B. And finally, compare the left-hand side and the right-hand side. Because y is the conditional expectation of x given a, we know that the expectation here equals the expectation here. So this tells us left-hand side equals the right-hand side as desired. So now we check the second condition. Okay, so this tells us the independence. Roughly speaking, it tells us if we know some information B that is independent of what we are interested, then this information doesn't help to calculate the expectation. Okay, so this is conditional expectation. Okay, final part of this first class. Let us calculate one precise example of conditional expectation. So this example, we can see in this example, we consider a sequence of independent random variables. And now we define a sigma algebra AN. It is Sn is the summation of this sequence up to time n. And An is all the information of Sn after Sn. So this An is all the information of Sn starting from n. So all information of Sn for n later than n. And the question is, what is the conditional expectation of x1 given all the information in An? Okay, so to calculate what is the conditional expectation here, so first let us check what's the relation between x1 and this An. So for this An, we know that it is the information of Sn plus 1 and Sn plus 2. And Sn plus 1 equals Sn plus Xn minus 1, plus 1. And this Sn plus 2 is Sn plus Xn plus 1 plus Xn plus 2. So the information of Sn plus 1 and Sn plus 2 is equivalent to the information that Sn and Xn plus 1, Xn plus 2. They are the same. Because we can reconstruct the sequence from here, and we can also reconstruct here from there. So these two algebras are the same. So this gives us the same information. And then we want to calculate the conditional expectation of x1 given An. And here we see that all the sequence here is independent of x1, because this is an IID sequence. So from independence property, we know that given all this part of the information, it doesn't help us to calculate the expectation. So given An to calculate x1 is equivalent to the information if we want to calculate x1, but only know the information of Sn. Because this part is independent of x1, and it's also independent of Sn. So it doesn't help us to calculate the conditional expectation. And now, in fact, we want to calculate what is the conditional expectation of x1 given all the information of Sn. So what is Sn? Sn is the summation from x1 to xn. And here we see that this sequence of xi is IID. So if we change x1 to some other index k between 1 and k, then the conditional expectation should be the same. So observation. So for all elements from x1 to xn, if we want to calculate the conditional expectation given Sn, they should be the same. And since all of them are the same, and we also know that x1 plus xn equals Sn. So this is what we know almost surely. And then we take conditional expectation to both sides. What we have is and here, for the left-hand side, because we just explained that for different k, they give the same conditional expectation. So for the left-hand side equals n times that conditional expectation of x1. And then for the right-hand side, so the right-hand side is the conditional expectation of Sn, given all the information of Sn. Of course, Sn is measurable with respect to itself. So the right-hand side is exactly this Sn. So since the left-hand side equals the right-hand side, we can conclude that the expectation of x1 given An equals the expectation of x1 given Sn, and which is just Sn over n. Okay, so this is the first part, probability space and the conditional expectation. And we will have a break. We will resume on 10:30, and it starts with Martingale.